So that was cool. So this is the supply to the most. And I guess this is where we'll get to supply to the most. So this is more of the coffee thing. Now you're not trying to save the world. I mean, you try to make people happy, kind of, but also while making lots of money, so it's a little complicated, you know. You make nice ads, but you still want all the people's money. And so you are probably not going to put a Starbucks out in the middle of nowhere, right? Yeah? You're just not going to do it. So that's okay. So this is a public versus private story, and this is work that came out of South Korea. Again, it's right, PNAS 2009, so it's within the last decade. You know, it's been really interesting. I mean, a lot of things I think I've showed you in both, yeah, Parks and, I mean, work just keeps coming along, right? It's not completely done yet, yeah. So this was cool. And so they say, well, this is Umadel, they say, in fact, you know, all of this stuff makes sense, but there's just been this kind of one criterion, which is making the average distance as small as possible, which is a very reasonable thing to do, but you know, maybe you just want as many people in the door as possible, right? So if you have, you know, one facility, then you're going to put it in the middle of New York City. If you have, you know, 10, you're going to really put them in cities, right? You're going to do that, you know, yeah. And as you add more and more and more, you're going to end up with things like McDonald's that are opposite each other on streets because they're franchises and it's really a real estate company and bad things happen and so on, right? So, but you will, right? You'll end up with a block that has 4 Starbucks on it in a really dense city. And people get upset, except for the people getting the coffee, right? And then the other people getting the money. Yeah, so, but it's yeah. So they point out, well, this is not completely universal. They have these sort of 2 end limits, and one is the for-profit version, which is going to be, you will really actually lay down things according to the density of. And I mean, if you got really excited, you put too many, right? Which I think was kind of achieved maybe in Manhattan around in the early 2000s, where there was just this proliferation of banks and like everywhere along Broadway, there was just like a bank every 3 doors, and there were also drugstores. Which in Australia is a pharmacist, because drugstore just doesn't sound like, it's just confusing. Okay, so really, you want to disambiguate those things. Okay, so, and then they all, you know, a bunch of them died out. They had a little war where they just went, you know, CVS just put in like, you know, store everywhere, and so did Rite Aid or whatever, and then a bunch of them gave up. It was very strange, but I think they over-densified. Anyway, so they have a nice thing. They say, well, okay, some examples, like that one over there is public schools. It's more 2/3-ish. Maybe it sort of picks up as the density of people goes up. I mean, of course, this is not, you know, this is 2 orders of magnitude. It's not much, but maybe it deviates. Sort of plausible, right? Super dense, so now it's out of control. And that happens in, you know, places like Manhattan where you're building up and it's more complicated. This is for ambulatory hospitals, which is weird to me, but anyway, this is, yeah, that's more like matching the density. That's the break-in scaling. Yeah. All right, so they end up with a nice plot like this. I mean, they make a whole table, and you know, when you get to these papers, you've got to be worried that because you never see all the plots underneath, right? That's it. These 2, yes, but who knows about these things? They do have their fits. Yes, they have their fits. That's all right. So you can see some of them are kind of rough, but there's a breakdown between US and South Korea, and they kind of have this. These are the ones that are more for profit, and I don't really know why hospitals there. And they have this really weird example down here. So fire stations, you know, this is kind of good, right? I mean, they need to be in places so they can, on average, get as fast as possible to problems. This is a really weird, this is basically 0 scaling, right? And this is a government structured thing where they just said they're going to be here, like just pure grid. So this is just really agnostic of any population density. So and of course it's a terrible fit. But the point is that these things are really just distributed in a way that doesn't pay any credence to where people are. Yeah, okay, what else we got in here? Post office for, oh, for either of them? I don't think they do have post office. You're right. You're right. It's interesting. You know, and there really isn't obviously there's a lot of, you know, there's somewhat messy fits. They've got this kind of rough transition around 0.8. They sort of, you know, they generally kind of make sense. But this, you know, this is, instead of just one thing, you know, they've got all this stuff right now. So it's much more, they realized it was more complicated and showed it was more complicated. They did a similar thing. They did the restructuring stuff. So, or maybe they didn't. No, they didn't do the diffusion thing. But this is give you a sense of the Voronoi cells. You know, the locations of things. This is the public schools and the hospitals. These ones are going to be, so the hospitals are more clustered in around where the population is, and public schools, hopefully you can see that they are spread out a little more. Is that true? It's hard to tell. Yeah, right? There's more structure in here. Yeah? You can see more structure in here? Yeah. More of an effort to help the people? Yeah. Okay. So that's cool. And so they play around with a thing, and I'll just sort of put this up here. This is a thing so we've got populations in cells, we've got the average distance within the cell, so it's related to what the others have done. Yep, don't worry about that. And then they say, well, now there's something we're going to minimize. It's going to be a mixture of this distance. Before that was just to a power of a half. Well, actually it was power of 1, I should say. It was area to a half. And then we're also going to include the population in there. And so the limits will be, 1, we're back to sort of purely social, and yeah, purely commercial when we don't care about how far people travel. And so if you go through that, you end up with this, right? So this is ad hoc. This is made up, right? This is an ad hoc little cost function. It's a way of dialing between two limits. It puts scaling, you know, scaling is in there so that when they solve the thing, you'll still get scaling laws. So that's, you know, definitely kind of made up. But you end up with this 2 over beta plus su, and that's nice. So beta equals 0. Alpha equals 1, right? The scaling is, right? So if we have a 0 here, this is 2 over 2, so the scaling is 1. So that matches with this commercial scaling story. So that's good, and it matches with their little micro mechanism, right? So there you didn't care, when b equals 0, you don't care how far people have to travel. That's not part of the cost function at all. It's just the number of people. When it's 1, then we really, you know, we care about it in a linear way, and we get this 2/3 scaling retrieved, right? Okay, so that's maybe an assignment question. But I need to sort out if I shoveled too much into POCs. Anyway, it's a beautiful body of work. But it does get to this point in time where it is a bit messier, right? This is great, it's well done, it's a bit messier, so we have to sort of, you know, there's still room to clean this up. But they definitely opened up the box and said, you know, it's not just this thing, there's definitely some scaling like this, here is a little story for it. Okay, so that's pretty good. So I think, obviously, this is where we're going to end. I will talk about a very important thing next, which is, so we're going to sort of move on from this whole optimal supply networks. We're going to talk about random networks, right? So random networks, again, introduced in POCs, just an incredibly important fundamental thing that we have to know about networks in general. There are the pure random networks from, this has been sort of well studied in graph theory, which is Erdős-Renyi, but it'll be a departure where we tend to understand that the degree distribution is incredibly important, so we'll fix that and then play with things on top. But we'll get things like bipartite structures and so on, and then some of this nice kind of work with eventually community detection, but also, you know, things like betweenness. So they're really sort of right. These are just really important pieces to know about networks in general. Okay? Okay. So there's an assignment due this Friday, which is really assignment 3, and there is a new one on deck, and I had the dates wrong, but it's due like a week from Friday. Also, I want to say about office hours, right? They're on now, and they go for sort of an hour, but people hang around, and I'm there, and so you should come along for the festival of office hours, and it's fun. All right, people, thank you. Next time we should have a counting of Winter Olympic things too, right? Like how we're doing.